Now that we have learned about the basics of the family of wave solutions we generated, and we looked at simple situations of the basic state being stationary or easterly or westerly. Let's add a little bit of realism to the solutions by looking at the meridional shear in the upper level winds and how that would affect the equatorial trapping latitudes and so on that we have been concerned about. So this is the upper level winds 200 hectopascal mean flow field with the turning latitude that we will see later on shown here with this red dashed line. The two regimes are defined here as the strong easterly winds in the upper atmosphere and the westerly regime here. So we can think of it as equatorial easterly regime and equatorial westerly regime, which obviously what we have been doing, except that now the flow is not constant in the meridional direction like before, but it's a function of y, a strong function of y. In fact, you can see the sharp gradients here. So if you look at the meridional section of the zonal wind at 140 west here, you have strong easterlies, easterlies going 140 easterlies, and then as you go beyond the Hadley cell, obviously you transition into westerlies, and then towards the pole you drop off and becomes maybe weak easterlies or so. This is your basic meridional section of the zonal winds. At 120 west here you have a slight difference in the deep tropics where you have westerlies and of course easterlies as well, but in this at this longitude you have land on the either side, so you get differences in the mid-latitude westerlies, which we will not worry about. We are basically worried about the tropics and then the turning latitude, which goes all the way up here. So you remember our basics already, what we have done. There is a very strong dependence of the equatorial trapping latitude on the background state. In this case, the background westerlies with much weaker meridional shear than the easterlies give us much larger scale of equatorial trapping compared to the easterlies, which restrict the waves to, much closer to the equator. So that's what we are doing here. I'm not going to read much here, but jumping right to the solutions, we are looking at eigenfrequencies in this shear flow we looked at. So we will look at basic state being stationary, compare it with equatorial easterlies and equatorial westerlies. So 140 east and 120 west. 140 east is almost over the Indonesian seas, New Guinea area. Almost over the maritime continent, I think, and 120 east is around Galapagos, close to Galapagos. Okay, so the impact of equatorial easterly shear tends to increase the eigenfrequency slightly for eastward modes, right? So, but reduce it for westward modes. Great changes occur in equatorial Rossby modes where the critical wave number K0, denoted by the red circle, tend to occur at larger scale. So equatorial Rossby waves, we are always worrying about low frequency, large scale waves which have got westward phase speed, and high frequency short scale waves which have eastward phase speed, right? So we are looking at that transition wave number here. So this is again our dispersion diagram of eigenfrequency versus zonal wave number and impact on different families of waves. Kelvin waves here, not a huge change based on the background shear, easterly shear. Similarly, the westward and eastward mixed Rossby gravity waves have somewhat larger impact than the Kelvin waves. So Kelvin wave still remains essentially non-dispersive eastward propagating wave, gravity wave in the background shear, whereas Western low frequency mixed Rossby gravity waves and the eastward mixed Rossby gravity waves have a larger impact in the equatorial westerlies compared to the equatorial easterlies. So you can see again the same process works that we talked about before. The westward and eastward inertial gravity waves have less impact at low frequencies than at high frequencies. So this is consistent with the meridional structure we had seen for high frequency waves, which goes out much further in westerly flow regime. So westerly flow regime on either end expands the frequency, the impact of westerly shear is much stronger, whereas in the westward regime it's somewhat less than here. Okay, what else can we say about it? Let's just go to the physics later on when it'll all become much clearer. So if you look at the meridional distribution of the geopotential for a particular zonal wave number of 5 for the first meridional mode, you can again see that when the basic state is stationary, it's much closely trapped to the equator, and amplitudes here are almost the same, but there isn't much impact of the easterly versus westerly upper regime, other than that they already have larger meridional scales in terms of the geopotential. Okay, what else can we say about that? So upper level winds do not affect the equatorial Rossby waves in the vertical so much, I guess. Mixed Rossby gravity waves, again similar message, easterly shear versus westerly shear compared to the basic state that is stationary, n equals 0 for the mixed Rossby gravity waves, of course, and the character of the mixed Rossby gravity waves and Kelvin waves don't change so much because they don't have such a strong effect in the easterly and westerly regime. So that does relate to how they respond to forcing at various frequencies and scales. So they bridge the gap from the low frequency equatorial wave, Rossby wave regime to the high frequency inertial gravity waves. Okay.